Bill Rocks on College Physics. We're going to be looking at some collisions. We've discussed the types of collisions. Just want to look at a couple and then do a couple problems involving some collisions and conservation of momentum. So I've got a couple carts right here that pretty freely can roll across this track. Just want to have a couple little examples of the different types of collisions. So really, we've got either they're going to stick together or they're not going to stick together. Perfectly inelastic or inelastic. We're not going to have conservation of total kinetic energy because there's sound being made, there's friction in the tracks, there's all sorts of stuff going on. But really just want to look at the collisions themselves. So these two carts, they're not quite the same mass. This one has a little bit more mass than this one. But there's this little plunger here, a little spring-loaded mechanism. Springs conserve energy, so I'm not really worried about the spring itself. And we can just see that these two objects can run into each other. They have some initial momentum as they travel in those directions. They collide, and then they do what they're going to do, right? So I could have one that's at rest. This one comes in, hits it. This one does what it's going to do. And this one comes in, hits it. This one continues moving. But in terms of the total momentum of the system, as long as we can treat this as isolated, which it's actually not, but it's pretty close, no external forces acting, then the total momentum of the system is conserved. So what I just want to do is look at a couple different things going on here. What happens if I make this one a lot more massive all of a sudden? So add some masses onto this one. I have this one at rest, and this one comes in and hits it. What happens? Well, it gives this one some momentum, and it continues to have momentum in the same direction. But it reduced its speed by some amount when it hit it, reducing its momentum. So it slows down, but it imparts momentum to this one. In terms of conservation, well, the total initial momentum was all substantiated by the mass times this one's velocity. It strikes this one, they both now have momentum, but the sum of those two momenta has to add up to be what the original momentum of this one had. Total initial momentum of the system equal to total final momentum of the system. Again, assuming an isolated system. So there's a couple different things that could happen, right? We could have this one comes in pretty fast, this one's coming in slow, and kind of see what happens. This one continues moving, this one changes its direction totally. A big change in its momentum, because again, momentum has the velocity vector, it's a vector quantity. Initially this momentum was that way, and then after the collision, the momentum of this green cart was in the opposite direction. Pretty big change. We could have that this one's moving fast and this one's moving kind of slow. What happens? Well, this one changes its direction still pretty drastically, and this one changes its direction. But it'd be such that, again, the total momentum of the system's conserved. So what else can we do with this? Well, without knocking stuff over, I can undo this spring here. I've actually got it so these two objects can stick together via some magnet. Excuse me, some magnets. So we can have this one's at rest, this one comes in, collides with it, they stick together. They form one common mass, and they have some final momentum was what was equal to the initial momentum of this one. Go ahead and reduce the mass of this one a little bit, and we can have this one's kind of moving slow, this one comes in, overtakes it, forms some common object. So the point with this is that with this perfectly inelastic collision, these two objects stick together and do what they're going to do, such that the total momentum of the system is a conserved quantity. So this one can be going slow, this one's going fast. The momentum continues going that way, in the direction of whatever momentum dominated directionally. So I just looked at a couple little things there. What I really want to do is pop out some problems here. Let's put this down, and let's go ahead and look at a problem involving conservation momentum and a couple objects interacting. So we're going to take two objects. Object with mass 1 being equal to 1 kilogram, and we'll say that its initial velocity, v1 initial hat, is going to be equal to 3 meters per second I hat. And we're going to take some mass number 2, that is going to be 2 kilograms of mass, and that its initial velocity, v2 initial, is equal to, what we're going to say, negative 3 meters per second I hat. So here's the actual problem. All right, there we go. So we got these two masses with these two initial velocities. They're going to collide. And in this part A, we had a perfectly inelastic collision. We want to know what's the final velocity of these masses. So we can draw this out, sort of. Assume this is some frictionless surface, if you will. We've got this V1 initial hat M1. We've got this M2 and a V2 initial hat traveling in opposite directions with these subsequent masses and velocities. This is the before. And then we've got the after the collision. Being that this is perfectly inelastic, let's kind of make this like this. We've got this M1, M2, and then we've got some V final hat. And we want to know, what is this? So all we've really got to go with is this is a perfectly inelastic collision and conservation of momentum. So we've got a delta p hat total is equal to 0, which gives us that M1 V1 initial hat plus M2 V2 initial hat must be equal to the quantity of M1 plus M2 times V final hat. Again, they stick together, forming one common mass with one common velocity. So we want to know what that V final is. That seems pretty easy to isolate, so let's just do that. We've got a V final hat is equal to the quantity M1 V1 initial hat plus M2 V2 initial hat divided by the quantity of M1 plus M2. So let's just go ahead and put in the values that we have, and note that again we've got to keep track of these as being vectors. So we've got 1 kilogram multiplied by the quantity of 3 meters per second squared. So say times 3 meters per second, excuse me, not squared, 3 meters per second I hat. And then we've got plus 2 kilograms times, we've got negative 3 meters per second I hat for velocity 2 initial. And that's all going to be divided by the total mass, M1 plus M2, which has to be equal to, you guessed it, 3 kilograms. So we look at this. This quantity here is going to be 3 kilogram meters per second I hat. This quantity here is going to be negative 6 kilogram meters per second I hat. So we've got 3 plus negative 6 divided by 3 here. So we've got negative 3 kilogram meters per second I hat divided by 3 kilograms, which is then equal to negative 1 meter per second I hat. This will ultimately substantiate conservation of linear momentum. These two objects collide, they interact, there's no external forces, and after the collision, we have to have that this V final is in the negative I hat direction with a speed of 1 meter per second. So this is equal to negative 1 meter per second I hat. That's what would happen if, again, momentum is conserved and these two objects collide under these conditions here. There we go. Why do they continue going that way? Well, these objects have the same speed, but this is twice the mass. Twice the mass, same speeds, twice the momentum. And ultimately, total momentum was in that direction initially and is in that direction finally. The same amounts, 3 kilogram meters per second, negative I hat direction. All right, so that was part A. Part B just says, hey, how much energy was lost in this collision? So we know that energy is lost because we're only considering the energy that was necessary to make these objects stick together. So really we just want to figure out what is delta KE total. It's going to tell us how much energy, how much change in kinetic energy there was. And we got that this will be equal to 1/2 M1 plus M2 times V final quantity squared. There's the total final kinetic energy minus the total initial kinetic energy, which is going to be 1/2 M1 V1 initial squared minus 1/2 M2 V2 initial squared. So we can put in all these quantities, right? We've we've got that's 1/2. This is going to be equal to 3 kilograms. This is 1 meter per second, negative 1 meter per second quantity squared. The negative sign doesn't really matter because we're squaring it. We got 1/2, 1 kilogram. This is 3 meters per second quantity squared. Minus 1/2, 2 kilograms times 3 meters per second. The negative quantity squared, the negative sign, sort of irrelevant there. And hope we can just go ahead and put this in the calculator really quick. We've got 1.5 times 1.5 minus, this is going to be 9 divided by 2, 4.5. We've got minus, this is going to be just minus 9. So we give ourselves 1.5 minus 4.5 minus negative 12 joules of energy. I'm forgetting this 1/2, that's why that looked weird. Oh, never mind. It was just 9, 4.5 minus 13. So we're plus 13.5. Minus 12 joules. There's a change in kinetic energy, so 12 joules of kinetic energy is lost, ultimately due to them sticking together. That's the amount of energy required to make these objects form one object. All right, so there is the perfectly inelastic collision case. Pretty straightforward. Let's look at a inelastic collision case. An easy one to begin with. And see what we can do with this. So we're going to take these same two objects with these same two initial velocities, 3 meters per second I hat and negative 3 meters per second I hat respectively. And then we're going to go ahead and say that V1 final hat is equal to negative 3.5 meters per second I hat. So this is what we've got. These two objects traveling towards each other, and we've got that M1 has some final velocity, V1 final hat, that's that way with a speed of 3.5 meters per second. And the question becomes, well, what's the final velocity of mass number 2? V2 final hat is equal to a what? All right, so this is what we observe. We want to figure out what the final velocity of mass number 2 must be. And again, we just start off with the fact that total momentum is going to be a conserved quantity. Delta P hat total is equal to 0. Thus we have M1 V1 initial hat plus M2 V2 initial hat equals M1 V1 final hat plus M2 V2 final hat. And that's what we want to figure out there, that V2 final hat. We'll isolate it, we can subtract this from both sides, divide by M2, and we've got ourselves the V2 final hat must be equal to the quantity of M1 V1 initial hat plus M2 V2 initial hat minus M1 V1 final hat quantity divided by M1. There we go. So let's just go ahead and compute this out here. We've got quantity of 1 kilogram times 3 meters per second I hat. And we've got plus 2 kilograms times negative 3 meters per second I hat, which we already know adds up to be negative 3 kilogram meters per second I hat. And then we've got a minus 1 kilogram times negative 3.5 meters per second I hat. So these two divided by 1 kilogram. These two momenta add up to be negative 3 kilogram meters per second I hat. Let's subtract off this, which is going to give us a positive 0.5 kilogram meters per second I hat, divided by 1, And we've got ourselves 0.5 kilogram meters per second I. So these two objects collide, and after doing so, this one is going in the opposite direction at a speed, at a rate of, well, 0.5 meters per second. That's it. So if this one's going to go that way at 3.5 meters per second, this one must be going that way at 0.5 meters per second. I shouldn't put kilograms there, because we're just looking for the final speed. There we go. So the question then is, well, how much energy was lost in this collision? What was the change in kinetic energy? So we can compute that out, much like we did before. Figure out what's going on here. Was energy gained? Was energy lost? We got to look to the change in kinetic energy. So we've got delta KE total is going to be equal to 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared. There's the total final kinetic energy. We subtract from that the total initial kinetic energy, which is 1/2 M1 V1 initial squared minus 1/2 M2 V2 initial squared. And that will be equal to the total change in kinetic energy, which we can go ahead and figure out now being equal to 1/2 times 1 kilogram times 3 meters per second quantity squared, excuse me. This is the final. We've got negative 3.5 meters per second quantity squared plus 1/2 times 2 kilograms times 0.5 meters per second quantity squared. There we go. We've got a minus 1/2 times a 1 kilogram times 3 meters per second quantity squared minus a 1/2 times 2 kilograms times initial was negative 3 meters per second quantity squared. Crunch this all out, and let's see what we get here. We've got ourselves 0.5 times 0.5 squared plus 5 squared minus 0.5 minus 1. We get ourselves negative 7.125. 5 squared. 5 squared. Yep. Negative 7.125. Negative 7.125 joules. So 7.125 joules of KE is lost. Lost in this collision. Where did it go? It was transformed into other forms. Heat, permanent deformation, sound. These are all transferences of energy or transformations of energy. So it was lost to something. There it is. Transformation gone in terms of kinetic energy, and that's the requirement for this particular system under those conditions of the final velocity of object number 1 being negative 3.5 meters per second I had. All right, that was a good one. We'll take a look at another one here that's a little bit more extensive, looking at an inelastic collision. Yeah, be right back. Let's do that. All right, here we go. We got another problem here. Here it is. Okay, so we've got ourselves two masses, M1 and M2, that are on a collision course. One dimension, isolated system. This would be some frictionless surface here, if it is a surface at all. And object number 1 going 8 meters per second to the right. Object number 2 going 7 meters per second to the left. before the collision. Then they collide. And we are told that 150 joules of energy is lost in the collision. So with this, we have delta KE total is going to be equal to, that's right, negative 150 joules. Energy lost, negative 150 joules. And then we have, after the collision, we have object number one is now going in the opposite direction that it originally was, going quite a bit slower, 3 meters per second. Object number two is going that way at 2 meters per second. The question is, what are the masses if this is the case? So what we got to figure out is how to approach this. There's energy lost. Their objects are not sticking together. This is an inelastic collision. Inelastic. So what do we have to go with? Well, again, we work under the assumption that this is an isolated system, as it was stated anyway, and we utilize conservation momentum and the fact that the total change in kinetic energy is equal to this to see if we can figure out what those two masses are. So let's spell some stuff out here, right? We've got ourselves delta P total. The total change in momentum has to be equal to 0. So the momentum of this system here, total, has to be equal to the total momentum of this system. So from this, we've got ourselves M1 V1 initial hat plus M2 V2 initial hat must be equal to M1 V1 final hat plus M2 V2 final hat. There's our conservation of total momentum there. So we're just told right and left in terms of directions, but right and left are opposite, right? So let's say to the right is plus, and let's say to the left is minus in terms of directions. We could say positive I hat and negative I hat, that would be fine too, but ultimately we need a sign that correlates the directionality of this, even in one dimension. So we're going to let right equal plus, left equal minus, directionally. So we've got that going for us. And what can we do with this? Well, we can't solve for M1 and M2. We've got two unknowns, right? We've only got one expression here, one expression and two things that we don't know. Well, that's not good. That's not going to help us by itself. But what else do we have? We've got ourselves delta KE total. Delta KE total, well, that's going to be equal to negative 150 joules. The delta KE total itself is the difference in the total final and total initial kinetic energies, which then has to be equal to 1/2 M1 V1 final squared plus 1/2 M2 V2 final squared minus 1/2 M1 V1 initial squared minus 1/2 M2 V2 initial squared. Here is the total final kinetic energy, and then this is negative of the total initial kinetic energy. Total final minus total initial. There's the change in total kinetic energy, which has to be equal to 150 joules. So now what do we have here? We've got two expressions, right? Two expressions, two unknowns. We should be able to use these two expressions that all involve the same quantities, M1, M2, V1 final, V2 final, V1 initial, V2 initial, and figure out what the two unknowns are. So that's it. That's the idea of this. So from here, it involves a bunch of algebra, which let's just start doing, right? So I'm going to take this first expression and start working with this one, because this one looks like it's going to be the easiest to find some sort of relation with. And what can we do with this? Well, we know the initials, we know the finals. What if we happen to put the M1s on one side and the M2s on the other side? So let's rewrite this. I'm going to move this term over here. I'm going to move this term over there. So we can write this as M1 V1 initial hat minus M1 V1 final hat is equal to M2 V2 final hat minus M2 V2 initial hat. Why do we want to do that? Well, we can factor out the M1 and the M2, and we can write this as M1 multiplied by V1 initial hat minus V2 initial hat is equal to M2 times V2 V2 final hat. Oops, I'm doing the initials. We got V1 initial, V1 final, V1 initial, V1 final, sorry. And then we've got V2 final minus V2 initial. All right, there we go. What does that allow us to do? Well, it allows us to look at what one is in terms of the other. Because now I can say this. Excuse me. I can say that M1 is equal to the ratio of the difference of these velocities divided by these velocities times M2. So M1 is equal to the quantity of V2 final hat minus V2 initial hat divided by V1 initial hat minus V1 final hat times M2. And we know what all these quantities are, right? So from this, we get ourselves that M1 is equal to, well, V2 final. V2 final, that's going to be 2 meters per second, which is to the right, which is positive then. So we've got ourselves 2 meters per second. And then we've got V2 initial. Well, V2 initial was 7 meters per second to the left. So we've got minus V2 initial, which was negative 7 meters per second. So there's that quantity. And then we look at V1 initial. Well, V1 initial was 8 meters per second to the right. The right is positive. So we've got ourselves 8 meters per second. And then we've got minus what? Minus V1 final. V1 final is 3 meters per second to the left. So minus negative 3 meters per second times M2. So what does this end up being? This is 9 and this is 11. So this tells us that M1 is equal to 9/11ths of M2. That is fantastic, because now if I know what M2 is, I know what M1 is, or vice versa. So all I got to do is figure out what one of those are, what one of those is. All right, so we go from there, right? Let us just start doing this. So this is what we get out of the conservation of momentum or relation. That must be the case. And then it's to figure out, well, what is one of those quantities? So now we look to the change in kinetic energy. And we've got this nice expression. Pull this back down. We've got this nice expression right here. Negative 150 joules is equal to KE1 final plus KE2 final minus KE1 initial minus KE2 initial. And we've also got that M1 is equal to 9/11ths of M2. Well, I can take this in and stick this in for M1 here and M1 here and rewrite this entire expression, so the only thing that I don't know is M2. And then what? We can solve that for M2. Once we know what M2 is, we get ourselves M1. So this here is going to get substituted in here and here. So we can rewrite the whole thing all in terms of the velocities that we know and M2. Solve it for M2. So let us rewrite this all out now. So we've got the delta KE is equal to negative 150 joules. And carefully now, that must be equal to 1/2 times M1. Well, M1 is 9/11ths of M2. 9/11ths M2 multiplied by V1 final squared. Well, V1 final is equal to 1 final. Hey, that's negative 3 meters per second. That quantity squared though, so that's negative sign's not going to really matter. Anyway, we've got that term, then we've got a plus 1/2 m2 times v2 final squared. Well, v2 final was 2 meters per second. That quantity is squared. So there we go. And now we've got a negative 1/2 m1 again. M1 is 9/11ths of m2. 9/11ths m2 times v1 initial squared. v1 initial was 8 meters per second. That quantity is squared. Minus 1/2 m2 times v2 initial, which was 7 meters per second quantity squared. So 150 joules has to add up to be equal to all of this here. Whew, that looks like a mess, but look at this. We got this common factor, m2, 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 m2. Everything else is just numbers. What happens if we factor out that m2 and divide negative 150 by what's left over here? We're done. Basically done. So let's just go ahead and do this. We will write this out kind of nicely to begin with. So I'm going to go ahead and just start here. And we can write that as 9 times 9, 81/11ths, 81 22nds. So we've got m2 multiplied by the quantity of, again, 9 times 9 divided by 11 times 1/2 gives us 81 22nds. I'm not going to worry about units. Let's start getting messy with all this. That's just going to be meters squared per second squared. That's fine. And then we've got this term here. We've got 4 divided by 2. That's just going to be 2. So plus 2. We've got this term here. We've got 8 squared. 64 times 9 divided by 22. 64 times 9. 576. Let's put it 576 22nds minus 576 22nds for this 8 squared times 9 divided by 22. And then we've got this right here. That's just going to be a 49 halves minus 49 halves is equal to negative 150 joules. Well, that's just a number there. Shall we just go ahead and quantify that out? Sure, let's just go ahead and do that. So we've got this is m2 multiplied by 81 22nds plus 2 minus 576 22nds minus 49 halves negative 45. That's a nice number, huh? Negative 45. And this again has to have units of meters squared per second squared. Meters squared per second squared. Let's go ahead and put them there. Is equal to negative 150 joules, which is kilogram meters squared per second squared. So this gives us the M2, not N, but M. M2 is equal to negative 150 divided by 45. Excuse me, negative 45. Negative 150 joules divided by negative 45 meters squared per second squared is going to give us, now we computed it out, 3.333. 3.333 kilograms. That has to be the mass of mass number 2. And from that, we can now get the mass of mass number 1 because we know mass number 1 is 9/11ths of mass number 2. M1 is equal to 9/11ths of M2, which is then 9/11ths of that, times 9 divided by 11, gives us 2.727. 2.727 kilograms. There we go. We're done. We figured out what the two masses have to be in order for those particular velocities to be the case before and after with that amount of energy being lost. Change the amount of energy lost, and change what the masses would have to be. So this is probably the simplest case where we have two unknowns. The other case would be we don't know what two velocities are. Generally, you don't know what the two final velocities are. It's the same method that you have to use, but it gets a lot more algebra because you got these square terms that have to expand out. But I'm sure you'll see something like that in homework. Maybe not, or an exam, possibly. Anyways, good problems, good fun, good math, good physics, good times. All right, that's it. Have a good one.